Welcome. So I have made this template code for direct volume rendering. And if you're interested in learning more about volume rendering, or maybe you just want a quick setup, you can use this. And in this video, I just want to go through the code as best as possible to give you a sort of an overview of everything. So a lot of this is, of course, based on teachings by Stefan Bruckner in a course on the University of Bergen. And also much of it is based on papers and also my own way of programming. So here's a brief overview of the code. So there's a main method, and the main method doesn't really do anything. So here is the main method. So of course this is C++, so it's using object-oriented programming scheme, right? So first of all, the main method is not doing anything really. It's constructing the system manager, which is the main class, the main object. And then it's just setting off this frame loop inside of system manager. So having a look at system manager here also, so you can see the main object is just making the system manager, and the system manager is constructing all of the other classes basically. So inside of system manager, first of all, I'm using glfw to handle the context and to create a window. And I included this link in case you would like to look at the documentation. So this is just the setup for how the context will, how it's defined. So it's defined to use OpenGL version 4.5. And yes, you can read more about this in the documentation. Also, I did not include any error handling. So if you need some error handling, you need to include it yourself. So it will create a main window using the glfw create window command. And it will get a size. And this is just a default size I have set. So if I execute it, this is what you get. So you get a window, and yes, and here's the size that was defined. Some more error handling stuff. And this one, make render context current. So when you create a window like this, you will, when you render your OpenGL, you use OpenGL to render, it will be rendered into the currently the current context, or like the context that has been made current. So if you want to have more than one window, let's say you would like to have two separate windows, you could just create one more window using this command, and then you would need to have a pointer to each of the windows, and then you would need to use this before rendering every time. So here you can see make render context current. It's basically just doing this function, make context current, and then it's passing in a pointer to the window, to that specific window that you created. So if you want, you could say like a second window equal gl create window, and so on, right? And then you could have a second window, and then before rendering into this window, you would need to do something like make second window context current, right? So this is a public, this is made public, so you can access it from outside this this class, and you would need to do that with the other one as well. I'm also using GL objects, which is just a wrapper API for GL binding. So you could just use GL binding, the GL binding API, and then you would just do your OpenGL commands as normal. But with these GL objects, you can do it. You can use these wrapper functions that are much easier and faster to write. And I will show more of this later. But when you initialize GL objects, you automatically initialize GL binding. So you don't need to do that individually. And here's I'll show you a example. Here is an example of a GL binding function. And this, while something like, let's see, something like this here would be GL objects. And doing something like this would be a lot more text, a lot more code if you use GL binding, the standard GL bindings instead of GL objects. But okay, so I'm using GL objects. I'm also, to get the interaction with the keyboard and mouse, I'm using GLFW, right? So that it's the GLFW window has this callback functionality. So if I, for instance, press space now, let's see, yes. It's a bit slow, I guess. But yeah, so why is it so slow? Huh. Usually when this window is active, I just press space and then it will print here, but maybe it's because I'm recording. But so yeah, keyboard and mouse interaction is using the callback functionality of the GLFW window. So yes, and I will show more of this later. And then, of course, I'm creating all the main objects. So the scene, the renderer volume, and the three directors here. Yeah, and of course the frame loop. So this is the main render loop, which is set off here after constructing. And so what it's doing, it's polling for input, the keyboard and mouse input, and then it's doing some GUI stuff here. I will explain this later. And then it's doing the main render function, which I also will show later. And this one needs to run after the frame render because it needs to render the GUI on top of the volumetric rendering. So it needs to be after this. And then, of course, swap buffers. So when you're rendering using OpenGL, you're always rendering to an image that isn't displayed on screen. And then when it's done, when it's ready to be viewed, you do swap buffers, and then you will start rendering to another image that isn't seen, right? So you're never rendering to the image you're actually displaying on screen. And then if you are, so this loop runs while the window is open, and if you close the window, it runs the shutdown function, which is will just destroy your window and terminate the context. So that's the system manager. Okay, so let's look at the scene first. So like I said, the system manager constructs the scene, and this scene will construct any object that is part of the scene. So in my logic, I feel the camera is part of the scene, so I have the camera in my scene. So we can have a look at scene first. Inside scene, yeah, so you can see you're just creating in the constructor for scene, it's passing a pointer to the system manager, and also it's creating the volume and the camera objects. And the reason I'm passing in system manager as a pointer is because in the way I like to do things is if I need to, if for instance this needs to communicate with this, it will just get a pointer to system manager, and then from system manager it will get a pointer to volume. So everything moves through system manager. So yeah. Update scene doesn't do anything. So here in the frame loop, you can see I have this. You shouldn't really update your scene in this way. I mean, it really depends on what you're doing, but you should usually just use your interaction to update variables. But in case you would like to do something that is automatic without interaction, for instance, animation, rotating your model, for instance, all the time, then you can just implement the logic here, and you can uncomment it. But yeah, so the scene, like I said, it constructs the volume, and the camera doesn't really do anything else, and it keeps it. And also it does have a scene matrix, but it's not being used for anything. And these two, I think I can just remove. Let's see if it still works. Yeah, it's because they are not being used in this. So, okay, the scene matrix, it's just a identity matrix. Okay, so the volume. Okay, so there's a bit more happening in the volume. So first of all, the constructor, so all my classes take a pointer to system manager, as I said, using it to connect with any other object in the program. And in here, there's a model matrix. So there's one matrix for the scene and one for the volume, which is the model. So I keep the model matrix in here. And first, it's just a identity matrix. But I do some more stuff with it. So as you can see, first of all, it's loading in the data. So this is the volumetric data. And the volume data, you can just change this to if you have a different data set that you want to use, you can change it. Change the file name here, and it needs to be a nifty file format. Okay, so the load nifty, well, it's using the nifty C libraries. So if you need to read documentation, you can look here. But basically, it's using the GL objects debug, which will print into your console. It's just saying telling you to wait for the nifty data to load, and then in case there's some data in memory, it will remove it, or in this the memory that is pointed to by this variable. It will remove it, and then it will read the file that was defined here. And of course, if it fails, it will print to your console. And then it will read the header of the nifty file. And I can show you how this looks like. If you set this to true, it will show the header on load. And so when you load it, now you can see all the information contained in the nifty header. So here you have dimensions, for instance, the dimensionality of the data, of the volumetric data. And there's a lot of stuff here. If you want to know about it, if you want to learn more about it, you can just check out the documentation. This one. This will tell you everything you need to know about all the header stuff. But yeah, I'm just gonna turn this off. Oh wait, so first of all, there's one thing you absolutely need to do. That is to scale the volume based on the header, like based on the scale of the nifty file. So what I'm doing here, I'm just taking the so I'm taking the dim, let's see here. I'm taking the first, second, and third value of the dim in the header and storing it into this variable. It's just a vector. And then I'm making this into a scale vector that I can use on the matrix, on the model matrix. So I'm storing the dimensions from the nifty header into a vector, a GLM vector. And then, so I'm doing this here, and then when I get to, so first, okay, let's go through the model matrix. So first of all, the model matrix is just the identity matrix. And then I'm translating it such that the origin is in 0. So if I did not do this, you can see that the volume anchor point is here. And that's not something you would like. You would like the anchor point to be in the middle of the volume. So now you can see it's anchored in the middle instead. And then I scale it using this scale vector that I got from the header dimensions. And yes, I'm just scaling this model matrix, and then this model matrix you will pass into your shader. Yes, scale, and then you need to do some extra translation after scaling to make it anchored in the middle. And then I'm also doing this get values from data, which is just a function that, let's see, get values from data. It's just, it's going, so I think it would be great if the biggest data value of the volume was contained in the header, but it's not in nifty files. So you have to iterate through all of your data and find it. So I'm just finding the biggest data value in the brute force way. I'm just going through all the values and checking for the biggest data value. I'm also saving the average data value just because I can. I mean, I'm not using it for anything in this template, but maybe you would like to use it for something. So it's available. So this would be a mean value. But yeah. Okay, so that's the volume. And this is not doing anything in this update volume. Okay. In the scene, yes, so you create the volume, and then you also create the camera. And the camera, it's the view and projection matrix. So if you want to change your if you want to change the view, for instance, rotate around like this, then now I'm changing the view matrix. Also, when you resize the window, you need to, so you can see it's resetting to here because I'm recalculating the view to make bigger size view. And it also recalculates the projection matrix, I think. Right. I'm just going to remove this header stuff. Let's see. Okay. So all the handling of the view and projection matrix is done in the camera. So if you want to recalculate, so okay, when you run the constructor, it's only doing this, recalculating the camera, which is setting the viewport size equal to the window, the GLFW window. But I mean, the reason I'm doing this is because maybe you would like the viewport, the rendering viewport, to be smaller than the GLFW window. Let's say you want to do something like this. So now you can see there's a gap here. So now the render window is only this big. Maybe you would like to have a GUI on this side here. And now it's easy to separate the 3D view from something else that you want. So you can use this. Yes, and also it's creating a view matrix, which is basically using the glm lookat command, taking a camera position, place you're looking at, and also the up vector of the camera. And all of this is set here. And if you can change this if you want a different view, default view position, but you have to remember also if you're setting this too big, you might not. Okay, yes, so you can. This is happening. This is because I have a limit for how long the ray tracer is working, or the ray march. And this is because my method of direct volume rendering that is currently implemented in the template is really bad. So, and this is something, of course, you would need to optimize or work on. But that's just something to keep in mind. Yes, so as I've mentioned, I'm using the GLM, which is OpenGL mathematics. And here is the documentation if you want to have a look at it. It does all this. You can make vectors and matrices, and you can do matrix and vector calculations and make camera, for instance, here. So this create view matrix is just running this simple GLM command, so it's very easy. This would be much harder without GLM. And also create projection matrix. You can just use this perspective and it will create the projection matrix for you, which makes it very easy to work with. And if you change this, you will change the angle, like the view angle of the projection. So I think this will maybe zoom in. Okay, this zooms out. Okay, yes. I think 45 is usually a nice angle. Okay, so that's the create view and projection matrix. So that is how you calculate your camera, your default camera. And then using the interaction, you can change. So here, for instance, using the mouse, I can rotate and zoom and change the position of the camera like this. I will come back to this later, how this works. Okay, so that's the camera. And that's the scene, basically. It's the volume and the camera. And then in the system manager, we are creating the renderer volume. And this, okay, let's see. Yeah. So the way this works, this is probably the most complicated function or the most complicated object. And this is where you will probably be spending most of your time, except for the shader, of course, when you're working on your direct volume renderer. So first of all, the constructor is just, so it's printing this little message, and then it's doing this setups. So it's doing these for setups. So I will try to explain them here. So setup screen geometry. So the way the direct volumetric rendering works is you are creating a quad that is sort of just pressed onto your camera. And this quad has a point here, 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 and here. And from these points, so this is the quad. It's with the points in 2D space, and then you create, using these points, you create indexes of two triangles. So you have one triangle that is 0, 1, 2, and one triangle that is 1, 3, 2. So that would be 0, 1, 2. This is one triangle, and then it will be one triangle here. And these two triangles is defining your quad, right? So it's this quad that is pressed onto your view. So you're not really using polygons when you're doing direct volume rendering. You're using something called image-based rendering, and what you're doing is in your vertex shader, you're not really doing anything, right? The only thing you're doing is passing on the positions onto your fragment shader. And inside your fragment shader, for every pixel on the screen, you will do your ray tracing. So you shoot a ray into the scene and do something with it. So you're not using polygons, and this is how this is why it's like this. You make a quad on this, a screen quad, and then this will create pixels, the individual pixels for you with their position in space, with correct position in space. So let's say I want to, if I do this, for instance, if I shrink down the quad size, now you can see it's only rendering this inner quad. So you could, if you wanted to, you could make a quad for the outside and one for the inside, and maybe you would, for instance, do higher fidelity rendering within this inner quad, which is what foveated rendering is if you're working with virtual reality, for instance. But yes, so that's the quad, the screen quad, and setting this to 1 will fill the screen. And then here you're just making this vertex buffer, which you are using when rendering in OpenGL. And I'm not going to explain this. The only thing I will say is, if you're on a Mac, this one will probably be the reason it's not working for you. If you have tried to run the code and it's not working, this will probably be the reason, and you might need to change this. Maybe I will change this in a later version. You can just ask me if you have problems with this in the comments, and I will try to help you. So that is the screen geometry. It's basically this screen quad that you are doing your like ray tracing on, the image-based rendering. And of course, you need to set up your shaders. And here I'm just using the GL objects shader, or this setup. This, I mean, if you didn't use GL objects, this would probably be 20 or 30 lines of code, I think. But here you can see it's just 5 lines of code, and it's really nice to use. If you want to learn more about this, you can look at the documentation. But so you're basically just passing in the vertex shader and the volume, the fragment shader, and then you generate a program, a rendering program out of this. And yes, you can, if you want to add more shaders, you can just add them in here, and you can change these. I mean, you need to have a vertex and it needs to be a vertex shader or a fragment shader, and you have to put it in the correct place. But yeah, so that's the shaders, and then set up volume texture. So the volume texture, well, all you have done so far in your volume class is load in your volume data, raw volume data. But you want to make this into a 3D texture and pass it into your fragment shader. So first of all, you need to have the correct dimensions, and this, right? So I pass in a pointer to the system manager, and here I'm just through my system manager, I'm just going to the scene, and then from the scene to the volume, and then in the volume I'm getting my dimensions. And then you create an empty object or empty texture, and then you're setting the parameters of this texture, and then you're using this. So this is GL objects wrapper functionality, and I'm using this one, and this will create a 3D texture for you. So you have to pass in the width, height, and depth, and also you have to pass in the data. So here I'm just getting a pointer to the data. Let's see, get volume data. Here it's just returning this. So when I loaded the Nifty, I loaded it into this variable. And now you can just do this. To get the data, you reference this, and then you use the data command. And then this will be the last input argument in this function, which is a pointer to data. It's a very nice way of doing it. And then you bind this 3D texture to your program. So you're setting this uniform called volume texture. And if you look in here, here is the uniform. And you have to use this bind command to bind this to the zero slot of textures. Okay, so, and then you have your volume texture ready to use inside your fragment shader. And the gradient texture, so I'm not using this at all in this template or in my fragment shader right now, but it's ready to be used. I think it should be working. I haven't tested, so I will figure out. If it doesn't work, I will update the code. In the future, I might make some videos showing how to use the gradient texture. But so the gradient texture is the exact same size as the volume texture. So you can use the same dimensions, and you need to make a compute program with shaders, a compute shader. And this is what I'm doing here. It's basically doing the same as here, but I'm using the compute gradient shader that I have here instead. And yes, just creating a compute shader program. And then you have to remember to use the program before you actually use it, or you have to call this that you actually want to use this program. Yes, and then you create an empty texture. So this is the 3D texture that will hold the gradients. And then I'm setting up all the parameters. And then I'm calling this again, creating a 3D texture. But instead of passing in data, you're just passing in a null pointer. So it doesn't have any pointer yet. There's no data yet, right? So you're creating an empty 3D texture. And then you bind your volume texture, the original one, and your empty gradient texture to your compute shader. And then, so you can see here, the volume texture is read-only, so you can't overwrite the values. And the gradient texture is write-only, so you can't read from the values. And this, I'm not sure exactly what would be the best group size when it comes to these work groups of the compute shader. I just know that 4 works pretty good, and also 8 I think would work pretty good. And you might want to change this depending on what you're doing. For this use case, this is fine. And then you actually call your compute shader program, and you perform your computation, and then it will do this. So here's the compute gradient, compute shader. In here, there is an input volume, which is the volume texture. Then it's output volume, which will be the gradient texture. And in here, what I am doing is this is a central difference calculation. So I can show you here from Stefan Bruckner's lectures. So the way this works, so a gradient is the vector pointing in the direction of largest function change. So for instance here, let's say this is your volume data, and this is empty space. So at this point, you would get this vector, and here you would get this vector. So it gives you both as iso surface of a position where you go from one space density to a different space density, and then the magnitude of this vector, like the size of this vector, will say how big the change is. So for instance, going into, let's say this is higher density values than this vector would be longer. And it's calculated using central difference, which is basically just doing this. For this vector, for instance, you take this value minus this value, which returns 0, this value minus this value, which returns a high value from here, and this will give you a vector with a high value in the x-axis and 0 value in the y-axis. Here, if you take this minus this, you will get a high value in the y-axis, and you take this minus this, you will get a low or like a high negative value in the x-axis, and then when you blend these, you get like a vector like this. So it's a very easy way to get these vectors that are showing the vector in which there is change, right? Change in the data values. And this you can use also for surface normals. So if you use a first hit algorithm and you would like to have the surface normal at your hit, you can just check this value and check the direction of the vector, and it will give you the surface normal. And then you can use this in your Phong shader, for instance, to calculate lighting on your local lighting on your surface or in your rendering. So this will give you, this is doing this central difference, right? It's doing this one here, and the gradient. Yeah, so it's giving you the gradient and also the magnitude. So what I'm doing here, I'm passing out a vec4 where the first tree is the gradient, and now it's not normalized. So you have to remember to normalize it before you use it as a surface vector in your shader. And also the magnitude. It's just taking the length of this gradient, in case you would like to just have the magnitude as a single value. But you don't really need to do this. You can just take the length of this. You could just pass out this and then take the length of the gradient in your shader. But if you pass it out as a separate value, you don't need to do this calculation every time you need it. So you will save some computation. And this compute shader, you only do once. So it's a nice way of saving some computational power or optimizing your code. And then, yes, so when you're done with your compute program, you have to release it, and then you're done with it. And then now you have your gradient texture, and you can pass it in. And in the fragment shader, it's passed in here as a separate texture. So now you have the volume texture, and you query this volume texture for the data values. But now you can query the gradient texture for the gradient at the same position, for instance. Yes. And so that's the setup for the renderer volume. And yes, in your loop, in your frame loop, you will be running this renderer volume render frame function. So this render frame, that is probably the most important one. So inside render frame, you can use your GL bindings functions. Yes, okay. So first of all, you will get the viewport size from your camera. And this is getting it from the camera, not from the GLFW context window. So you can set a different camera size, right? And then you need to run this. So this is making the rendering go from 0, 0 to this width and this height. So you will fill out the entire window. If you want to have something like a quad view render style, for instance, you could do something like this. So this is your width and height. Now you can see it's only using this lower quad, and now you could render a different quad here, different quad here, different quad here, if you want to have a quad view. Okay. Here you just set up the OpenGL state, how it will be doing its or if it will be using depth, the depth mask. So in this code, it's using a depth buffer, so you can blend it with other renderings and use the depth buffer. I'm not going to go into much detail on this, maybe a different time. Okay, and then you say you want to use your rendering program, your direct volume rendering program. And then you run this update uniforms. So, okay, inside update uniforms, you are passing in all your values into your shader. So here I'm just generating a model view projection matrix and an inverse model view projection matrix, and I'm only passing them in separately. So I'm passing in these. If you would like your model matrix or projection matrix or whatever in as an individual matrix, you could just do something like this. Set uniform, and then you could say, yeah, model matrix, and then you could pass in your model matrix. So if you need this separately, and you might, depends on what you're doing. And also all the individual uniforms. So all of these are set using the GUI. So I'm defining them here. These are the interactive variables. To change these, you use the InGUI class, and I will show this later. But yes, so you update your uniforms, and then you run the draw function, which will run your fragment shader and actually render the image on screen. And yes, I will come back to this. So let's have a look at the interaction. So as I said, so that's the render frame. So there is also this interactor keyboard and mouse, these two, and this is these are pulled for in this glfw pull events. So inside interactive keyboard is not really anything happening. It's only doing this debug. So in the constructor, it is setting up the key callbacks. And so inside the key callback, here you can set up all your keys. So if you want to add a new key, you can just copy this and change the key, right? And then you can change the functionality here. So you can say you perform your functionality in here. This could be, for instance, changing some value here. Maybe you could also use it to, for instance, reset the camera position to front view, side view, top view, whatever, right? And so this is easy to do. And right now it's just doing this debug. So if I press space, for some reason I have to activate the window to make it actually happen. I don't know why. It should happen immediately. Okay, so that's the keyboard. So here you can just add functionality. And then the interactive mouse is basically the same. Instead of keys, you have your cursor position callback. So this is called every time your mouse position in the window is changed. So let's say we do GL objects debug and pass in the X position like this. Now you can see, same happening. I think it's because I'm recording, but this should be updating as I'm running my mouse there. Right, so let's see. Yes, right. So you get your mouse position on screen. Okay. And what it's doing now, it's just running this function in the camera. And yeah, so let's see. First, so it's running this one on the cursor when the cursor changes, and when you push your mouse button, it is running this one in the camera class, and when you use your scroll wheel, it's calling this function in your camera class. So first of all, the mouse cursor position event, as you can see, it's doing something depending on some if statements there. So if this one is activated, it's doing this rotation functionality. If panning is activated, it's doing this panning, and if zooming is activated, it's doing this zoom functionality. And so these booleans are activated using the mouse button event. So when you push your mouse button, it will call this function and pass in the button and the action of the button, which the action is just a boolean saying if it's being held or released. So and that's just true or false. So In case of the left button, which is the button 0, so it's setting it to the action. And then if you're holding in here, if you're holding your mouse button and moving your mouse cursor, you can see you're rotating around. And also, let's see, so that's the rotation. If you hold your right mouse button, you do the panning. And if you use your scroll wheel, you would just be moving in and out of the scene. And yes, there is also a middle hold. You can hold your middle mouse button and do this to zoom also. So, I mean, this should be easy to understand. And then this one is called when you use your mouse scroll wheel, which is this one. Yes. So that's the interaction for the mouse and keyboard. And then there's also the GUI interaction. So the GUI interactor, first of all, the constructor, you don't really need to understand this so much. This is just taken from the ImGUI documentation. You can change this font if you want. So if you change this font, you pass in the new font name here. And this begin frame and end frame, these are just taken from the documentation, and also this render UI. What's important to know is that you need to do the begin frame first, and then your end frame. And the end frame needs to come after the direct volume rendering to render on top. If you did this before the volume rendering, you can see the GUI is gone. So it needs to happen after. And this draw menu is the one you will need to change. So here is where you will be defining your menu. So for instance, for my volume, so this one, the file menu is not really doing anything right now. So if you want to add saving and loading, you need to change this with load and save functionality. Exit one is made, however, this one works. And then for the volume, for the render style, all of these. So first of all, if you want to learn more about this, you can go to this. This is a very good documentation of the ImGUI system, and everything you need to know is in there. But so how it works is you define this type of interaction in. So first you make your this menu position. You say where you want it to be placed in your menu. You create this new tab in your menu, and then within this tab you can create these sliders, for instance, and it can be buttons or whatever you need. And how it works is you give it a name, and you need to pass in the address to the variable you want to be changing. And so here I'm just passing in a pointer to march distance within the renderer volume. So within this class, here it is. So this, let's see, march distance, this one. So I'm just creating it here with a default value, and then this default value will be the default value when in the menu also. So here's the default value, but now I can change it. And then this value is passed in here, right? For instance, this is the march distance, this one. And then this is passed on to the fragment shader. Here. And now you can use it in their shader. So this is how it's all built up. And if you want to add a new, variable, you can just say, so you add it here. Maybe you say, yes, I don't know, redness equals 0.0. Then you have this, and then to change it, you would make something like this. Then you would have a pointer or get address of this redness. And then you could set them the minimal value. And let's say the max is 1.0. And then, yes, how many decimal numbers you want. Let's say 0.3. And I think that's all you need. And now you have a new slider here. Let's see. 0.0. Oh, this now needs to be F. Yes, so now you have a slider. And then in here, you have this one. And to pass it on to your shader, you would say set uniform. Maybe you call it redness there as well. That, and then in here, you would form float redness. I think it needs to be the same. If you put a capital R, it needs to be capital R here as well. And then if you set up this variable in here to do some changes in your shader, it will work. So yes, that's how that works. Let's see. Just gonna remove all this. That's how you add a variable. And this is how these work, right? All of them. And then in your renderer, so you are, when you draw, you're using this shader here. So as I mentioned earlier, the vertex shader doesn't do anything. It's just passing on the positions. And so inside the fragment shader, let's see, let's keep these two open. In the fragment shader, I mean, maybe I'll make a different video on this. Okay, it's not so much happening here. So first of all, it's generating this for each pixel. This is happening for every pixel on your screen. First of all, you're making array origin position, which is the pixel, where the pixel on the screen is in the scene. So if you put your screen into the scene, the pixel would be positioned on this position, the ray origin. And then the ray direction would be a normalized vector pointing in the direction of the ray, of the view ray. And this is defined by this projection matrix. The angle of this vector will be defined by the projection matrix. And so to segment the volume, yes, so you could segment the volume. I am not segmenting the volume. What I'm doing here is basically just setting a start and exit point. And so it will go for 5 OpenGL units into the space before it stops, which is why if you set your camera too far away, it won't render anything, right, like this. This is a very basic way of doing it. It's not a good way of doing it. So what you should do is maybe you want to make a box, for instance, that encompasses your volume data, and then you use ray and box intersection, some algorithm to find your enter and exit point into this box, this encompassing box. And maybe I will make a separate video on this topic, or you can just read my master's thesis, of course. And then to get the color, it is doing this direct volume render. And how this works. So you're defining your maximum distance. So, okay, first of all, you need your ray origin and the direction you're traveling, and enter and exit points. And so the maximum distance is the exit point minus the enter point, the length of this vector. You start at no distance traveled at all, and then this will be the color that is accumulated as you step along the ray, and this is the color and opacity at the current position. So you have to accumulate your color and opacity, and you also need to get the current color and current opacity at a position along the ray. And the direct volume rendering loop, so it's just you have your ray origin and you have your ray direction, and then you step along the ray, and on every position you will sample your texture, and if you want, you can also sample your gradient texture, right? You could say float gradient texture value equals texture gradient texture current position. This should give you the gradient texture value at that position. So no, it's not doing anything, but I mean, you could use this. Well, let's try. Okay, let's see what's happening first, and I'll try to use it. So first of all, it's doing this transfer function. So it's passing in this value, the volume texture value, and based on this value, it's returning a color. And this transfer function, I'm not gonna explain it right now. In a different video, I can explain it. So basically, you're just passing in a data value, and based on the data value, it will return a color to be added to the composite. And then the current color. So the current color is set to this, the color that is returned from the transfer function and the current opacity is set to the opacity returned from this transfer function. And then you use this alpha compositing to add the color into your accumulated color and opacity. And if you reach a full opacity along the way, you can just stop early. You don't need to continue along the way. And so this is how this direct volume rendering works. This is a really, really, really basic volume renderer. And yes, so if I do this, and maybe I can multiply it in here. Let's see what happens. Yeah, you get nothing. Let's see. Yeah, now if you change this, so maybe I'll make it a little bit more. Yeah, so now you can see it's being multiplied with this gradient magnitude. Wait, okay, this is not. I need to do. No, wait. Yeah, okay, it shouldn't be this. It should be W, I think. Yes. So now you're getting the gradient. So now it's basically using the surface, or like the isosurface value, or the is using the gradient magnitude to define the opacity at that position. Let's see. If I change this, it's not the best example. Okay, let's just look at the difference. Let's see how it looks with it on. Oh. Let's do one more time. Let's see. There is with it using the gradient magnitude. And if I'm not using it, yeah, so you can see it's a bit different. If you use the gradient magnitude, it will accentuate the surfaces where the data values are changing from one position to the next. I need to explain this better in a different video, I think, because this video is getting very long now. Yeah, so I think I'll stop it there. Hopefully this will have given you some a little bit of overview of the code. Of course, you can ask me questions in the comments if there's anything you're wondering about. But I think looking here, this is a good overview of the code. This image is included in the GitHub repo as well, and you can always consult this. So it's very simplistic. You can add any classes to this as you need. I don't think you need to add many classes to this if you're just looking to do direct volume rendering, looking to learn more about direct volume rendering, or research some new methods. So yeah, hopefully this was helpful for you. Okay, thank you. Bye.